Sorry. Okay, we're about to get started. I guess we're starting. Welcome to the July 2025 General Meeting of the Mount Diablo Astronomical Society. Thank you all for being here. Our agenda this evening, I'm going to just do some quick introductions, and then our member Kent Richardson is going to talk about Vera C. Ruman, the astronomer, and her legacy. So that should be exciting. Then we'll have a 10-minute break for snacks. I see you guys have already broken in. So have I. Sorry for those on Zoom, you're missing out. And then we'll have our main speaker, Dr. White. Just a couple quick announcements. We had our society, the public night the last couple weekends ago. That went really well. Lots of adults at that one, not as many kids. So that was fun to see. Our next society night is going to be August 18th. And then, public night. Next Society Week is this next observings for the Society is this upcoming July 26th, and then also Saturday, August 23rd on the top of the mountain. The imaging group meets on Zoom every Monday, the second Monday of the month, second or third. Next meeting is August 18th on Zoom. All this is in the newsletter to sign up, and then the next general meeting will be August 26th. I still have some cards up here for the public astronomy nights. If anybody needs those for outreach, they have the dates on them. They're really fun. You can just hand them out to people and get them interested. Exciting Yosemite Star Party. Anybody going to that? Yeah, okay, we got a few. It'll be really fun, so looking forward. I've never been to Glacier Point. I'm going to be there this year for my first time. And then we've also got Barcroft at the end of next month, and then CalSTARS in September. Okay, Kent, I think we're ready for you. If anybody's new and needs the restroom, they're through those doors there. Do we have any new members tonight? Okay, well, welcome. Thanks for coming. Okay, this one back. Sorry. Okay, try it now, Kent.
How's that? Hello? Maybe I got a clip in
Test,
there.
test. Test, test. No. I apologize for more squealing. Okay. You guys saw it working for me, right?
It was, yeah.
Test. I don't understand. I apologize. Maybe this time.
worked for me before
Test,
when I
test.
was up
Ah, this guy died. Okay. Test. Plan D.
How's that? All right. Okay. Vera C. Rubin, a name that's been in the news lately for a number of reasons. Vera was born in Philadelphia in 1928 and grew up there, attended high school there. A well-meaning science teacher, when she graduated, recommended that she not pursue science, that she study art instead. She promptly ignored that and enrolled at Vassar College, which was known for some breakthrough astronomy. She got an astronomy degree, but for some reason, she was the only graduate the year that she matriculated. From there, she tried to, I need to advance. There we go. She applied to Princeton. They rejected her. They never accepted women in the astronomy program until 1975, if you can believe that. So she went to Cornell. And about that time, she was preparing to get married. Her husband was in graduate studies at Cornell, so that's the prime reason why she chose to go there. But they didn't offer astronomy, so she got a MS in physics. And from there, she got her PhD eventually at Georgetown. Her career was begun at Georgetown, but she soon joined Carnegie Institute in the Department of Terrestrial Magnetism. That's one I couldn't figure out. What's that got to do with astronomy? She established a collaboration with a fellow by the name of Kent Ford, nice name. Actually, that was his middle name, though. He was an astronomer and also an instrument maker. He developed a image tube spectrograph. And she did a lot of work in collaboration with him. She applied to become the first female astronomer at Palomar, but she was told they didn't have a women's restroom, so she'd have to limit her observing time. So she promptly went and cut out a triangle of paper, went to the restroom, taped it over the legs of the male figure and said, "There, now you have a ladies' room," and got to work. She was initiating faculty member of Vatican Observatory, and she gave dedication remarks for the opening of the Vatican telescope. She retired from Carnegie in 2014. Her research, primarily throughout her career, focused on galaxies. She had a controversial theory regarding galaxies, clusters. She said they clump together, but it's what we know as galaxy clusters. Galaxies cluster much like stars. With the image tube spectrograph, she could do a lot better detailed research and discovery of galaxies, particularly the Andromeda galaxy, but others as well. She spent a whole decade taking hundreds of observations. There's a picture of her there using the Kitt Peak 36-inch telescope, and that tubular thing in front of her is Kent Ford's image tube spectroscope. In her studies, she discovered there was an apparent anisotropy in the expansion of the universe. Isotropy suggests everything is the same in along the same direction, but in different directions, it could be different. A good example is a tree trunk. The vertical cross section, or excuse me, the vertical makeup of the tree is different than when you cut through at a cross section. Another example is the cosmic microwave background. That's an anisotropy of microwave temperature. We're all familiar with that. Her discovery was eventually called large-scale streaming. It was on the scale of 100 million light years. She also was very interested in galactic rotation. She observed the rotation of spiral galaxies and found flat rotation curves. I don't know if you can see the pointer here. This dashed line is what you would expect from the visible light from the disk and the mass associated with it. What she found, though, was the actual rotation followed a much flatter curve, like there was some missing mass. This was the first persuasive result supporting the theory of dark matter. She calculated that galaxies must contain 5 to 10 times as much mass than is observed by the visible matter. But now let's rewind about 35 years. Fritz Zwicky, a Swiss astronomer who spent most of his career at Caltech, was studying the Coma galaxy cluster. And he noted that there was a gravitational anomaly in the cluster between the galaxies. He used something called a virial theorem, which expresses a relationship between the kinetic energy of motion and the potential energy of the system of particles, or in this case, galaxies. So he came to the same conclusion. There's something strange out there. He came up with the term dunkle materie, and that means, guess what? Dark matter. So he is actually the first one to coin the term, but it was Vera that found more conclusive evidence within galaxies themselves, not to mention the space between them. She was very active in activism for women in astronomy. I told you about their high school teacher telling her to avoid science in the ladies' restroom at the Palomar. She wasn't allowed to meet her advisor at Georgetown, who's a male. It's also a Catholic college. She couldn't meet him in his own office. They had to find a neutral meeting point. And she was very concerned about the low number of women elected each year to the National Academy of Sciences. Some of the things that she did was to encourage girls in investigating the universe to pursue their dreams. She, fellow women astronomers described her as one that paved the way for other women. Rebecca Oppenheimer was given some mentorship by Rubin and considered that as important to her own early career. And she, in addition to astronomy, she fought for women's recognition in all sciences and science literacy. By 1963, I mentioned her planned marriage. By 1963, she had 4 children, and was doing a lot of work from home. That was pretty unusual at that time. She had what she called a unique part-time, full-time position at Georgetown. All of her 4 children earned PhDs in natural sciences or mathematics, and they recalled that her mother made science appear to be fun. In the early 2000s, not too long ago, she was still doing scientific work. And in 2013, articles with her involvement were still being published. She died of natural causes in 2016. Her legacy, first of all, she was snubbed by the Nobel Committee. A lot of people thought that was an egregious oversight, particularly fellow women astronomers. Not sure why that occurred, because there were women before her that earned Nobel Prizes. Marie Curie, one of the earliest ones, got 2. But meanwhile, we've got now the Vera C. Rubin Observatory, and I'm sure you've been seeing pictures in the media coming from that. That houses the world's largest digital camera for astronomy. We're talking gigapixels. And that was originally called the Legacy Synoptic Survey Telescope. And they later renamed the observatory itself after Vera Rubin. The telescope itself with that camera is named after some of the benefactors that put up big bucks to help build it, which, by the way, was built right here in the Bay Area at SLAC National Accelerator Lab. In 2002, Discover magazine recognized her as one of 50 most important women. And just this past May, Astronomy magazine had an article and listed Rubin as one of the 10 women who changed astronomy. And indeed, she changed it. There's a satellite named for her, man-made satellite. There's an area on Mars, there's a picture of it, Vera Rubin Ridge. And there's an asteroid, 5726, named Rubin. She got innumerable awards. Unfortunately, this doesn't show the highlighting that I have on my slide that came up. A few notable ones are the James Craig Watson Medal of the National Academy of Sciences, the Catherine Wolfe Bruce Gold Medal of the Astronomical Society of the Pacific. She was a member of the Pontifical Academy of Sciences. She's got a couple lectureships that she was granted. She has the National Medical of Science Award, and she was granted honorary doctorates from Harvard, Yale, Smith, Grinnell, and finally, Princeton, who had rejected her. Oh, here's the highlighting. I don't know why that came out twice. That's weird. She was honored on a 2025 U.S. quarter. It was the last year that the series of quarters on American women was produced. In 2024, I thought this was amazing. NVIDIA announced that the next generation of data center accelerators would be named after her, with a CPU named Vera and a GPU named Rubin. The Carnegie Institute has created a postdoctoral research fund in Rubin's honor. And then the American Astronomical Society Division on Dynamical Astronomy has named the Vera Rubin Early Career Prize. In the media, she was featured in an episode of Star Trek Discovery, in that they had a nebula named Vera Rubin. She wrote a children's book called The Stuff Between the Stars, how Vera Rubin discovered most of the universe. Excuse me, she didn't write it. She was also featured in an animated segment of the 13th and final episode of Cosmos, A Space-Time Odyssey. That was the redo of the one by Carl Sagan, which was hosted by Neil deGrasse Tyson. Publications. She wrote one book, Bright Galaxies, Dark Matters, Masters of Modern Physics. She published over 150 scientific papers. These 7, though, represent what were considered her most important writings by the Contributions of 20th Century Women to Physics project. Quotations. She saw nothing to keep her science and her religion from being at odds. She kept them separate, but thought she could live up to both. She was Jewish, so she saw her religion as a moral code and a kind of history, and she tried to do her science in the same, in a moral way. Don't let people keep you down for silly reasons, such as who you are, which she encountered in quite a bit. And don't worry about prizes and fame. I don't think she was terribly upset about not getting a Nobel Prize, although others were. The real prize is in finding something new out there. At age 10, she developed an interest in astronomy while watching stars from her window. Her father helped her build a crude telescope. But even then, she said, I was more interested in the question than the answer. And here's my references. Any questions? Thank you.
My question is about Rebecca Oppenheimer. I never heard of her. Is she another astronomer, or is she related to Robert Oppenheimer? Or?
I believe I forgot to research that, but I believe so. I also forgot to mention when she got the one of the awards. Oh, Royal Astronomical Society in Great Britain. She was only the second woman to ever receive that. And it was 161 years after Caroline, the name escapes me. Herschel. She was a sister, younger sister of William Herschel. So it took that long. She was an astronomer herself, Caroline Herschel, as was her husband, her brother, of course. Any others?
Any other questions? Okay.
Yes.
Is Alan Rubin, Professor Alan Rubin at UCLA, one of her children? He's a meteorologist.
Yeah, I don't have the names of her children. It could be. Her husband's name was Robert. Yeah. He's since passed.
Yeah.
But it could be that that's one of her children.
It could be there. Thank you.
Donna on Zoom said, thank you very much. Very interesting. Any questions on Zoom or any other questions from the audience?
By the way, the subject of the Vera Rubin Observatory, I think, is great fodder for a future What's Up. I'd like to see somebody pick up the challenge.
Okay, we're going to take a 10-minute break. Thank you very much, Kent.
Can I just pull this out, or do I need to eject it?
Yeah, it doesn't.
Yeah, I know. It always complains.
Paranoid, yeah. Like,
So does Mac OS.
I think I'm gonna so that you don't have to. I'm gonna like,
Yes. I mean, what we had up there was fine, I think. Yeah.
well,
I-
if I plug you in here and you just share your screen, or you could just share your screen. I think, yeah.
Well, shall I just share it and build it in?
So let's.
I guess stop. Yeah, stop sharing on that.
Yeah, because as long as you share your Zoom screen, they can see it on Zoom. Oh, but you don't have a Google
Actually, I do. It's all around here. If you want, maybe
So
we can.
let's move my computer. I'm gonna have you. Oh no, you want to sit on this side.
Well, no. I mean, if that's not long enough, then yeah. Here, I'll get it closer. All right. Yes, plenty.
There's always some technical glitch. It's hysterical.
Okay.
Okay, we're going to get started with the main speaker. We have Dr. Oliver White. He's from SETI and NASA Ames. He's been a planetary scientist at the SETI Institute, although resident at NASA Ames Research Center. So he's a double cover. Since 2017, his research focuses on unraveling the geological histories of the planets and moons in our solar system and learning how their surface has evolved. A member of New Horizons missions team, he is particularly interested in the icy outer solar system worlds and has produced a geographical map of Pluto to be published by the U.S. Geological Survey. He is currently creating similar maps of Saturn's moon, Tethys. I knew I was to say that wrong. Okay, everybody, welcome Dr. Oliver White.
Oh. Okay. Now is that?
I didn't pray hard enough.
Oh, there. All right. Okay. And thank you very much, Tara. And it's great to be here. Thank you for inviting me. So it's kind of, as sort of a team member on New Horizons who was there 10 years ago, it's hard to believe that 10 years have passed since New Horizons flew past the Pluto system. Just last week, I presented a much shorter version of this talk at the Applied Physics Laboratory in Maryland, where New Horizons was built. So we had a conference there, just sort of kind of reviewing the state of knowledge of the Pluto system after 10 years, both of New Horizons observations, but also Earth-based observations, and just recently James Webb Space Telescope observations. So I think one way in which things have advanced a lot is that Pluto was, of course, just a blob before New Horizons, and now we've created these geological maps of Pluto and its largest moon, Charon. So I've been leading the effort to create a geologic map. So these are essentially tools which we can learn about the histories of these planetary bodies. So for this talk, I'm going to sort of introduce you to the mission and then lead you on a tour through the histories of both Pluto and Charon using the geologic maps that have been made for them. So just a brief recap of sort of Pluto's discovery. It was discovered back in 1930 by Clyde Tombaugh at the Flagstaff Observatory, Lowell Observatory in Flagstaff. There was sort of a search for a planet X back then, and it was kind of an excruciating way to search for something you didn't even know existed. You essentially had to take pictures of a certain part of the sky, a star field, several days apart, and then you'd blink them back and forth to see if any of the dots had changed position, in which case it was not a star in the background, but actually an object in our solar system that had been moving between the between the several days between the plates being taken. So he did indeed find this object in 1930. These plates were taken 6 days apart, and this was then declared the ninth planet. Eventually realized it wasn't really the planet X that Percival Lowell had in mind, but it was called Pluto. And honestly, sort of further discoveries about it, because it was so small and far away, were not kind of few and far between for the rest of the 20th century. So, I mean, the best imaging we had New Horizons is from the Hubble Space Telescope. It's, again, like I mentioned, kind of a fuzzy blob. By the end of the Voyager mission to the outer planets, the 8 of the original 9 classical planets had been discovered. And so Pluto, out in the distant edge of the solar system, was the last of the 9 not yet seen. So there were quite a few efforts sort of in the 90s and to get a mission to Pluto mounted, and eventually New Horizons did succeed. Sort of is selected. This is the spacecraft here. It's about the size of a small grand piano, and eventually in July the 14th, 2015, is when it flew by. But just, a bit of knowledge about what we did know about Pluto before New Horizons. So we now know that Pluto is the first object to be discovered in the Kuiper belt. So this enormous disk of thousands of these little icy bodies orbiting between Neptune. I think 1992 was only when the second Kuiper belt object was discovered. So it took several decades between Pluto and the next one. And as of course, many of us know, the fact that it's part of the solar system with many similar small objects is why it was demoted to dwarf planet in 2006. That's all I'm really going to say about its planetary status, but if there's any more questions at the end, yeah. And so, yes, I mean, it was discovered soon after it was discovered, it was realized it was kind of different to the other planets. It has this orbital eccentricity, so its orbit is quite elliptical of 0.25. Those of most of the other planets are very circular, and it also has an inclination to the ecliptic, sort of the plane that the sun makes in the sky of 17 degrees. So it's all both quite eccentric and quite inclined to those of the other planets. And here it's some of its stats. It goes from about 29 to 49 astronomical units. So astronomical unit is the distance between the Earth and the Sun, so an average of 39, or about 5.9 billion kilometers. We did discover in 1978 its largest moon, Charon, was discovered, about half the diameter of Pluto, and actually Nix and Hydra were found with the Hubble Space Telescope, I think in the early 2000s, and then Styx and Kerberos, these other 2 tiny moons, were actually found while New Horizons was already en route to Pluto. So an interesting thing about the Pluto-Charon system is that it's somewhat similar to Earth-Moon system, and that the parent body and the moon is quite similar in mass. Pluto and Charon are actually much more similar in mass to Earth and Earth's moon, so much so that the orbit of Charon around Pluto, Charon doesn't actually orbit around Pluto, rather they both orbit around this barycenter, sort of at the center of mass of the Pluto-Charon system, with Pluto describing a small circle and Charon a larger one. So that's why it's off, and they orbit each other once every 6.5 days. So that's why it's thought of as the classic binary planetary system in the solar system, as opposed to really an Earth-Moon system. As for Pluto itself, so we can see them to scale with Earth here. About 2,400 kilometers across for Pluto, and about half that for Charon. With Hubble, I mean, we could tell there was a lot of brightness contrast across the surface, a lot of very dark areas and some apparently very bright areas, but we couldn't actually resolve any sort of geological structure or such. We were able, with ground-based sort of spectroscopy, determine that there were some quite exotic ices on its surface, not just water ice, but also nitrogen and methane ice. It's cold enough out at Pluto for those to be stable on its surface. And in 1998, we also found that, rather surprisingly for such a small object, there's a thin nitrogen atmosphere confirmed by a stellar occultation. So you sort of see a star pass behind Pluto, and you can see the gradual decline in the light from the star, which indicated that Pluto is surrounded by this sort of gaseous cloak, hence it has an atmosphere. And for an object of its size, it was sort of hypothesized back then that it was probably differentiated into a rocky center and sort of an icy mantle, and it may well have a water ocean, perhaps sort of helped to remain liquid by ammonia, which would sort of be a sort of an anti-freeze that would allow it to stay colder, stay liquid at colder temperatures than it normally could. But then, after 85 years, since Clyde Tombaugh discovered it, we finally got our close-up images. It went for a fuzzy ball to a fully fledged world in the space of just a few days in July of 2015. We weren't really sure. We had made some predictions before about what we might see. I mean, we knew there were these exotic ices, and there might be some funky sort of like sublimation features, sort of the ice sort of sublimating into the atmosphere and redepositing, and probably most likely impact craters. But what we saw just kind of blew all those predictions out of the water. We thought such a small object so far away, it would be in an energy-starved environment. There wouldn't be that much going on these days. It would be mostly geologically dead. But instead, we were sort of greeted by sort of this incredible geological diversity across its surface. We were all sort of like feasting on it like vultures when the first images came back, wondering what on earth is this, what on earth is that. And so it was, yeah, kind of a joyous experience, getting better and better data down and considering what on earth created, sort of formed this amazing world. So just in terms of sort of what we actually saw, and also this governs sort of what the geologic map looks like. This was a flyby mission. It basically was launched, I think it flew by at sort of 15 or so kilometers per second, maybe faster than that relative to Pluto. So it kind of zipped by in and over several hours the day of closest approach. It just took as much high resolution data it could. It came to within 12,500 kilometers of Pluto's surface, and you can sort of see in this little animation here, it sort of shows what would have been the view from the horizons. It sort of slows down as it gets close up to Pluto, and then it zooms off farther out into the Kuiper belt. So what that means is that we only saw one side of Pluto close up on that day of closest approach. What I call the near side is defined as the part that we saw better than a kilometer per pixel. The rest of it was seen at a sort of increasingly rubbish resolution from 2 to 40 kilometers per pixel in like the week or so as it was approaching Pluto. Yes, it got fairly rubbishy resolution here and getting increasingly better until we saw all of the near side at good resolution. But another thing to consider about Pluto is that it's its axial tilt, its obliquity. Earth's is quite moderate at 23 degrees, but Pluto, at the time it flew by, is at the extreme 119 degrees. It rotates on its side, kind of like the planet Uranus. And when New Horizons was flying by Pluto, the northern hemisphere is entering summer, the southern hemisphere is entering winter, and that means that pretty much all these southern latitudes were in constant darkness. So basically, these latitudes experience 124 years of constant darkness until summer comes back around, and then they'll experience 124 years of constant sunlight. At the extreme latitudes, that is, the low latitudes of Pluto do feature a constant diurnal cycle, 6.5 Earth days of sun, then 6.5 days of night. So yes, most of the southern latitudes we didn't see, although you notice there's like a strip here. Thanks to Pluto's atmosphere, we actually were able to see past the terminator, the day-night line on Pluto. The haze layers in the atmosphere dimly illuminated the night side. So it turns out we did get a bit of bonus mapping, high-resolution bonus mapping in that night side strip there. So we got a lot of nice images, but ideally you need a bit more than that to help sort of determine what's going on and make a geologic map. One thing is topography. It definitely helps to know what's high and what's low. So for a mission like this, you basically have to take stereo images. So take pictures of the same landscape at different angles, and the parallax means that you can you can construct a stereo map of the surface. So everything, the white stuff here is stuff that's high, and the stuff that's dark is low. That was only for the near side. For the far side, you don't have that luxury. It's too low resolution. But we do have, as it flew by Pluto, it can actually see the sort of mountains illuminated on the limb of Pluto, sort of with the haze layers sort of scattering sunlight behind. So you do actually get a few sporadic limb profiles to tell in a few spots what's going on with the topography on the far side. And it also carried this Ralph instrument, which contained these instruments, LISA and MVIC, that mapped mapped surface of Pluto at different wavelengths of light. So basically, these are spectroscopic observations. They're sensitive to the wavelengths that bounced off, sort of absorbed by Pluto and bounced off, those that are bounced off back to the spacecraft, and that basically gives you an idea of what materials are on the surface. So these are maps of different sort of spectral indicators of different materials on the surface, like methane, nitrogen, water, and also this stuff I'll talk about later, this red material here. So basically, yes, I used all this information, imaging, topography, composition, whatever we could really scrounge from the data we got to make this. This is the geologic map of Pluto. So the equatorial low latitudes are shown in Mercator projection here, and the north North Pole is shown in polar projection here. And I mapped 36 geologic units because it's such a chasm in data quality between the near and far sides. We figured it was prudent to map 6 separate units for the far side, even though ultimately I don't think there's anything on the far side that isn't already represented on the near side, but also tectonic lineations, so fractures across the surface, like our very own San Andreas fault, and also impact craters. And you can't really see it here, but that stuff I mentioned, the red material, the mapped as like a sort of an overlay on the surface here. And the southernmost parts of the imaging area I thought were a bit too rubbishy to map, so I sort of left that unmapped. And hopefully by the end of this year, this will be published as a US Geological Survey Science Investigations map, so the first official geologic map of Pluto. So I should just mention what exactly this is. So a geologic map is essentially a cartographic history of a planet's surface. Each of these colors is a geologic unit. Each has sort of a distinct texture, topography, composition, color, brightness that indicates a distinct, a unique sort of genesis and modification history for that particular landscape. And an important thing to consider is that when you're mapping this, you're not just thinking in 2D, like this stuff is over here and that stuff is over there. You're also thinking in 4D, just like what units are overlying others, and therefore what units are older and younger than other units. So again, it's essentially, yes, you're building up a geologic history of the planetary surface in map form, and it's essentially a way of sort of compressing down the sort of the often great complexity of planetary surfaces into comprehensible proportions. It's kind of sort of an art in a way, in that you try and represent the history as accurately as possible, as economically as possible, maybe not sort of like not like splitting it into too many units such that it's sort of just too much going on, but also maybe not oversimplifying things too much. Like there are some, in case there are like some units that are maybe sort of better separated to tell the history. It's, yeah, you would separate them. So it's, yeah, some mappers, some maybe tend to be slightly more lumpers, some tend to be slightly more splitters, but through peer review, we end up at something that I guess satisfies everyone. And so this is what we derive from it. This is the stratigraphic column, the correlation of map units. So each of these colors is one of the units I've mapped, and it's shown as bars. And these bars, their lengths indicate the timescales of their genesis and modification, with older stuff at the bottom and younger stuff at the top. Some things of their formation has been confined just to the older ages, the older part of Pluto's history. Some very young, and some things like craters have just been smacking into it to some degree, sort of from the very old times to the very young times. So we construct using cross-cutting and superposition relations to define relative ages. Basically, what that means is you look at the boundaries between units, and you can see if one unit, its boundary is like cross-cutting to others, that suggests it formed earlier. Like if you have a lava flow, for instance, that comes creeping across two other rock units together, then it would sort of cut it across, create like a T-junction, and you can see that that lava flow is superposing the other stuff, and so you can say that lava flow is younger than the other stuff. But another tool we use is also crater counts. So it's a general rule in the solar system that the more cratered a planetary surface is, the older it is. The idea that like in the early part of the solar system, there was lots of debris flying around and smacking into surfaces and creating lots of craters. And if nothing has really happened to those surfaces since then the craters just stay there, and you have an ancient surface, like our moon surface, you can tell is very old because of all the craters. But if you have an active geology at the surface, like we do on Earth, then that will eliminate those craters and generate sort of a surface with just very few low spatial density of craters, like our own Earth. So we can do that for Pluto. This is a plot we called an R plot. Each of these is a unit, and each of the dots represents sort of the density of craters on it. So in this case, it's actually young stuff at the bottom, old stuff at the top. So that's kind of the only way we really have by sort of estimating like the impact flux in the early solar system to actually get any absolute ages as opposed to relative ones. So I've used this to define these 4 geologic periods for Plutonian history. Each period is sort of host to a particular suite of processes that created major geologic provinces across Pluto's surfaces. They're called the Bernian, the oldest, from more than 4 billion to 3 billion years old, the Hayabusan, about 3 to 2 billion years old, the Tartaran, 2 to 50 million years old, and then the Sputnikian, which is less than 50 million years, and as we'll see, it's even modifying, changing before our eyes right today. So we're sort of going to start from oldest to youngest with the Bernian period. So this is the map sort of shown in a slightly different projection, and the Bernian units mostly concentrated on the western near side, so sort of where I've got these Bs here, these kind of purplish and bluish units. And this was by far the most active part of Pluto's geologic history. There are lots of sort of major events happening here and just a lot of very different sort of processes happening. So again, a lot of debris flying around in the early solar system, and so a lot of Pluto's impact craters formed during this early period, including this, which I'll focus on soon, this Sputnik Basin here, by far Pluto's largest impact feature. Once this formed, it was infilled with most of Pluto's nitrogen ice, these yellow units here. The emergence of this incredibly wacky tectonic system called the ridge-trough system, shown in purple here, going sort of across the equator here and then up over the pole here. The carving of these enormous Sputnik mountain blocks shown in brown here. And then Highlands glaciation, nitrogen ice glaciers carving into the ridge-trough system and also around Sputnik here. And then also deposition of, we think, methane-rich mantling material across much of the sort of fairly flat area of Pluto's western near side. So I'll just go through some of these things. So probably the most important thing to have happened in Pluto's history is the formation of this gigantic impact basin. It's slightly elliptical, so it was probably a kind of a slightly oblique impact to the surface, making this giant elliptical basin 1,400 by 1,200 kilometers across. So here's some imaging here, and you can see red high and blue low. This is this giant scar of this basin here, although interestingly, we can sort of trace its rim fairly well around most of its circumference, or its perimeter, but it's kind of missing an absent southern rim here. It's kind of these plains that empty out sort of farther to the south there. This white stuff you can see here, this is all nitrogen ice plains. So nitrogen ice in Pluto's atmospheric conditions, it will preferentially deposit from the atmosphere at low elevations. So once this enormously wide and also enormously deep, maybe as much as like 10 kilometers deep basin formed on the surface, it acted as a very powerful cold trap for pretty much all of Pluto's nitrogen ice that all collected in this giant basin. And it's actually remained there to this very day, pretty much all of it. There's some scatterings about sort of in a few other craters, but most of it is here. So that was one thing. It basically just formed this giant reservoir for all of Pluto's nitrogen ice. But we also noticed something interesting about its location on Pluto's surface. Sputnik Planitia is located, it's sort of pretty much its center is located pretty much right at the sort of at the anti-Charon point on Pluto's surface. So this little animation here shows the tidal axis between Pluto and Charon. I should have mentioned they're both tidally locked to each other, like the Earth's moon is tidally locked to Earth. They always present the same face to each other. So this anti-Charon side is always facing away from Charon. But we noticed that, yeah, given this enormous basin is located sort of at the anti-Charon point, the geophysicists amongst us argued that this giant basin is actually a mass excess on Pluto, and that basically when you have a mass excess, it will gradually shift the location of the rotation pole such that it is such that the mass excess ends up at the equator, and in something like a sort of a binary planet system like Pluto and Charon, it will also tend towards the tidal axis here. So we realized, I mentioned before, that we thought that Pluto might have a subsurface water ocean, and this was actually regarded as sort of some strongest evidence that it does have an ocean. If you have this giant basin forming, and if it has a subsurface water ocean, it will kind of uplift and thin the water ice crust to compensate for this sort of giant mass deficit formed by the basin. And in combination with all this nitrogen ice filling the basin, it would create a mass excess on Pluto and basically cause what we call true polar wander, the shifting of a rotation axis when you have sort of when you have a sort of a redistribution of mass such that the mass excess ends up sort of at this sort of low energy state, sort of at the tidal axis here. So that's, in that sense, yeah, being a giant repository for its nitrogen ice and also being the instigator for true polar wander of Pluto makes this arguably perhaps the most important event in its history. As for the map, I'm sort of indicating its rim sort of with this yellow line here. The edge of the basin has been since then been very much modified around its whole perimeter. There's not really anywhere I'd say is unmodified basin material, but I think some of the stuff that's been the least modified is this sort of HR unit here, this sort of purplish unit here that is very cratered and also home to actually this other impact basin, Burney, which is what the Burney is named after. So yeah, I think this is probably, out of anywhere around the rim, this is probably some of the best preserved material anywhere there. The other really sort of bizarre and grandiose feature of the Burney is this thing, this ridge trough system. So this is a giant tectonic system, but it's not just a simple crack in the ground. It's basically an enormous sort of mostly kind of uplifted, but in some places sort of down thrust, sort of band that stretches across Pluto from sort of far in the south. In fact, we're not actually sure how long it is because it actually drops off the sort of the night side into the night side of Pluto, but it stretches from there up to the North Pole over about 3,200 kilometers long and about 450 to 900 kilometers wide. So it's yes, it's a serious tectonic feature, and it expresses, again, it's not a simple crack. It expresses itself quite differently along its length. This is the topography map of Pluto that's reoriented such that the trough system is sort of oriented from left to right, and it sort of has it's very eroded. It has all these faults, graben, which is where you have two faults sort of on either side of a sunken block. Lots of ridges, mountain ranges, plateaus, tilted blocks, and also these things, these sort of ovoid, elongate depressions. On the map, I've represented it by 3 units, sort of that show different sort of ways in which different relief and different ways it's been eroded and tectonized. So these sort of purple units extending here. So what it is, it's a global scale tectonic system that is aligned along a great circle. It's sort of stretching along like stretching along Pluto's circumference, but kind of oriented in like a northeast southwest direction. So I mentioned it's heavily sort of modified. A lot of it seems to be modified, we think, by glaciation. We see a lot of these valleys, what we call them dissected, sort of its various components, where it sort of has these these valleys, stubby valleys cutting into them, like these mountains here in the dark equatorial region, sort of these other valleys around the North Pole. And this is kind of a good example, sort of in the mid-latitudes, there's this sinuous valley here. So as we'll go on to see later, we think that these valleys were carved by ancient nitrogen ice glaciers. Nitrogen ice, it's one of the exotic ices on the surface of Pluto, and it's unusual because it's quite runny. It has quite a low viscosity, so it actually sort of flow quite readily at Pluto surface conditions. So we think this stuff is really the only stuff that had the sort of requisite low viscosity, the only ice on Pluto that could have carved these things. I mean, one thing that's odd about it is like, what actually is this system? And we're not really all that sure. One of my fellow scientists has sort of invoked this process called equatorial crust or thickening. The idea is that Pluto underwent true polar wander after the Sputnik basin formed. This thing may actually have been on the original equator of Pluto, and I'm not quite sure how it works, but somehow like freezing of its subsurface ocean may cause it to thicken along the equator. Yes, I'm not sure. That probably requires a bit more modeling and thought, but I would say for the moment it's kind of a bit enigmatic as to how exactly this impressive system formed. But one thing, one consequence of its formation, it's created some of the most impressive landforms on Pluto in the form of these mountains, these blocky mountains that stretch in these mountain ranges along the west side of the nitrogen ice plains of Sputnik Planitia. So you can see some close-up of them here. That's kind of these big blocky mountains. They reach up to 5 kilometers high above the surrounding plains. That's like the height of Kilimanjaro above the African plains. They're mostly collected in these sort of these ranges here, but there are a few of them that are isolated sort of in the plains out here from the rest of the pack. But my mapping shows that the ridge trough system intersects Sputnik Planitia along most of Sputnik Planitia's western boundary here. So what we think happened is that after sort of Sputnik formed from all the nitrogen ice entering this basin and the ridge trough system formed, it basically heavily tectonized, it fractured the edge of the basin here, which was already pretty smashed up from having this giant impact into it. And then this low viscosity nitrogen ice from Sputnik, as well as Highlands glaciation, intruded and broke off bits of Pluto's water ice crust, because Pluto's outer layer is mostly water ice. Things like nitrogen ice is sort of just a veneer around the edge, and it basically just left these crustal fragments of water ice sitting in this sort of giant log jam at the shallow edge of the Sputnik Planitia basin here. But given that nitrogen ice is slightly denser than water ice, in fact, it's the same density contrast between liquid water and water ice on Earth, we think it's actually quite feasible that some of these smaller blocks here out in the center of Sputnik are actually floating in the nitrogen ice here. So it's basically water ice floating in a nitrogen ice sea, if you will. So yeah, nothing we could have anticipated before the flyby. And then we get to so we're still on the Bernian. Remember, there's a lot of stuff going on during this time, but now we get to the sort of heavily cratered western part of the near side. And this is maybe arguably what we sort of expected Pluto to look like most before we flew by. Lots of craters and what looks like some sort of evidence of deposition of a mantle, basically a few hundred meters thick deposit. We think of methane ice rich material here. That sort of deposit was originally gaseous in Pluto's atmosphere and just settled out across the surface to form this layer a few hundred meters thick, and it's arguably best seen where it's actually eroded. Maybe some of the methane rich material has again sublimated, gone straight from a solid into a gas into the atmosphere and left it sort of looking quite fretted here. So I've mapped it as this light blue material here, with sort of the darker shade of blue being where I think it's sort of been especially denuded by this sublimation. We also see a lot of Pluto's sort of more moderate, sort of smaller scale tectonics here, quite well preserved, like Inanna and Dumuzi fossae here. So these are extensional fractures. Pretty much all of Pluto's tectonism is extensional, and we think that's more evidence for a subsurface ocean. If you have a subsurface water ocean that gradually freezes, it expands when it freezes, and so it causes Pluto to basically burst its skin, forming these extensional fractures across its surface. And I think even this knobby sort of mantle morphology can actually extend even into this dark terrain. When you sort of stretch the contrast, it sort of have this sort of knobby sort of texture here that I think is a continuation of this mantle. And then in this sort of very low angle view looking out across the far west, this area here, Vega Terra, I think this is part of Pluto that hasn't really had, it's sort of these smooth cratered plains, but I don't really see any evidence for mantling. And I think maybe this is some of the most primitive side of Pluto we've yet seen that hasn't really had anything happen to it, like sublimation or glaciation, or really that much in the way of tectonism. So it may have actually kind of stayed pretty much the same for the last 4.5 billion years. There's one odd location here, sort of a subdivision of this dark blue unit here, sort of called Lunacod Planitia. So it's shown in this image. You can see it in the foreground here, and it has this what we call a sort of an erosional scarp called Piri-Rupes around here. This is an odd little patch of plains because it has very few small craters there. We think the small craters were removed by especially strong sublimation of a mantling material there that basically kind of sandblasted, if you will, a lot of its small craters away. Although exactly why that was such a sort of sublimation was so concentrated there, we're not really all that sure. So, okay, now we're going on to, that's all the first kind of billion or billion and a half so years of Pluto's history. Now we're sort of at the end of the Permian period, so we had the Sputnik Basin formed, it filled with nitrogen ice, and the ridge trough system formed, and you have some degree of true polar wander shifting Pluto to its current orientation. So after that, all of that stuff I showed in the West kind of remained the same. There wasn't really any much more large-scale geologic activity, but it was a very different story to the east of Sputnik Planitia, where we see successive, very thick, very major mantling events. And the first of these, in these units shown in purple here, are what I call the Hayabusan units, defining the Hayabusan period. So all of these, they're kind of moderately cratered. I mean, there are dozens and dozens to the west, but here there are only like sort of a dozen or a few dozen or so. So yeah, this area kind of dates from Pluto's middle-aged, and as I say here, it's witnessed this deposition and erosion of this methane-rich mantle, I think probably hundreds of meters thick. So might be a little hard to see at the back, but this is sort of what this looks like, this mantle. It's what we say has an accrescence texture. Basically, the texture of this terrain, it's quite sort of rounded and smooth, and maybe you can see it a little better in the topography map here, but basically we think this formed where you had a crescence of methane onto the landscape. A crescence is basically where you sort of just get coating of the whole surface of a landscape. It's like if you leave your freezer too cold, it sort of builds up freezer frost on it, like sort of these sort of pillow-like sort of formations. And we think that's kind of what's gone on here. Sort of it's coated this landscape, which I'll also note is sort of interrupted by these enormous pits and depressions here. Some of them are elongate, sort of aligned in chains, and we think follow the lines of sort of stress in the crust, sort of follow along similar orientations as fault lines in the area. Some of these large ones, they can't really just be due to sublimation. They're too large scale, so they may be due to actual sort of collapse of the surface here. And this in Pioneer Terra, sort of up northeast of Sputnik here, is where this mantle is best expressed. But across much of the rest of Hayabusa Terra, which is what the Hayabusan era is named after, it's in rather worse shape. It has the same sort of gently undulating large-scale topography, but on a small scale of like kilometers, it's much more pitted and fretted. So we think it's probably been eaten away by ongoing sublimation since much of the mantle since it formed. So that's the Hayabusan sort of that occurred to the east of Sputnik in the Hayabusan period. But then we have the most impressive deposition event in Pluto's history, which is the formation of the Tartaran deposits, which are shown in green here, extending from east of Sputnik edge here all the way round sort of the far side. So these are really, you only see a few craters here, so these definitely date from the last few billion years of Pluto's history. And these methane deposits are much, much thicker, like several kilometers thick, I think possibly even like 5 kilometers in some parts. So this is, just the most massive deposition event we've seen on Pluto. And I'll also talk about these things in a few slides as well, this orange stuff. But this is the stuff I'm talking about in green, these Tartaran massive methane deposits. We've called them bladed terrain deposits because they, on a large scale, these things form these sort of elongate, smooth, round-topped ridges you can sort of see here. But at a smaller scale, they have this kind of odd north-south aligned ridged texture that can reach sort of typically several hundred meters high. So we think that at some point in sort of in Pluto's sort of early, more recent history, a few billion years ago, there was a massive episode of deposition of methane from the atmosphere that caused just these enormously thick deposits to form in Pluto's equatorial regions here. That eventually the climate changed and favored more sublimation, and that basically sort of stopped deposition and caused the methane ice to sublimate away and caused this sort of smaller scale sort of bladed texture to form as the methane sublimated away. And I think that, so I think this sort of minty colored unit over here, this sort of shows a kind of similar texture to the bladed terrain, but you can see it's kind of been inundated by these sort of white, these sort of smooth plains here, which I think is ponded nitrogen ice that's deposited onto the bladed deposits here and kind of eroded them through glacial flow. We'll see glaciers much more in better views in the coming slides. But we think, so I mentioned that these things we think is a sublimation texture. We've actually compared them to sort of high altitude sublimation textures on Earth. These are called penitentes. They sort of form at low latitude typically, and high elevation snowpacks, and these all these little ridges are like pointing towards the sun here, sort of at its noontime position in the sky. And we sort of think that a similar thing is happening with this sort of jagged texture of the methane deposits on Pluto, just at a much larger scale, kilometers instead of meters, and with a very different ice at play, methane ice instead of water ice. So those are the bladed terrain deposits on the near side. Using help from our limb profiles, topography on the far side, and also spectral maps of methane, we've actually think that this stuff, actually the western edge is just the tip of the iceberg, so to speak, and that these things actually extend sort of around sort of practically half of Pluto's equator here. So really a massive amount of material represented here. And then we come to this stuff. So this is we're now south of Planitia. We're in this orange unit here I've called mounded material, and this stuff represents some of the most enigmatic terrain we've seen on Pluto, and I think probably might remain that way for quite a while until we can eventually go back. But this is home to these two unique mountains, Wright Mons and Picard Mons, which immediately caught our eye because they're very wide. Like Wright Mons is about 150 kilometers wide, but they have these enormous central depressions. In fact, they're so large, these depressions, it's almost like giant holes surrounded by mountains. And us being some simplistic planetary geologists, when we see mountains with holes in the top, we naturally think volcanoes. So that's kind of what the hypothesis that has stuck to date. We're thinking they may have a volcanic origin, but instead of sort of silicate lavas, rocky lavas being erupted at thousands of degrees centigrade, there would actually be cryolavas, water ice-based lava erupting at sort of very chilly temperatures. But I guess just an issue with this idea is that these depressions are so large, they're really much larger compared to the size of the mountain than any sort of large volcanoes we see in the inner solar system. So like this is Mauna Loa in Hawaii, for comparison, shown to scale with Wright Mons. You can see it's just got a tiny little caldera at the top compared to this enormous hole of Wright Mons, which you could pretty much turn Mauna Loa upside down and it would fit nicely into Wright Mons. So that's just one issue, just the bulk morphology is quite different for these things. Looking up closer, you can see Wright Mons has this sort of hummocky topography at a scale of like 10 kilometers, and also these little rimless depressions and sort of some like domical features that crop up and sort of interrupt this hummocky texture. We've sort of wondered if these is like sort of the equivalent to like oceanic pillow basalts on Earth, where you have basalt erupt on the ocean floor and extrude, create these sort of individual pillows. I mean, the fact is we can't really identify any sort of lava flow fronts or even any obvious source vents. So if this really is what we call cryovolcanism, we're not exactly sure how it would proceed. Cryovolcanism is kind of a field that's sort of in its infancy because we haven't seen that many obvious explicit examples in, icy place around the,
Would there be something to do with tidal forces?
Not really, there isn't really any, because Pluto and Charon, they orbit around each other and they're tidally locked there's no sort of changing gravity field that would inflict sort of strong tidal forces like you get at Jupiter's moons, where they're all moving relative to each other and they have a lot of squeezing. So no, we think that if there's the power source for this, it might, I mean, it may be partly just the remaining radioactive elements sort of creating heat in Pluto's interior, and maybe the sort of the freezing of its ocean creates an overpressure that squeezes it out. The problem with cryovolcanism is that liquid water is denser than water ice, so it won't rise on its own like lavas on Earth. You actually have to find a way to force it out. But yeah, given that these are very steep features, it's likely that water is the main component of these things. So yeah, I mean, we've had some thoughts too that maybe they are sort of like lava domes, each of these things, or maybe there's some sort of gaseous eruptions from these holes that are like sort of redepositing across the surface. But yeah, I don't think we're going to have a good idea until maybe we see a bit more of Pluto and advance like some treatment in the laboratory of these weird ices. And then we come to the last period on Pluto, the Sputnikian period. So this is basically all of Pluto's nitrogen ice deposits. I mentioned that like Sputnik Planitia formed very early in Pluto's history, but this surface is continually renewing to the present day. Nitrogen ice, it's very easily mobilized in Pluto's environment. It readily sublimates and redeposits on the surface, like I mentioned, sort of in this part of the bladed terrain deposits here. So yeah, it's constantly on the move, and like we only saw a few impact craters in the Tartaran, but you see absolutely no impact craters on any of these yellow units. Nitrogen ice is just too mobile. Any crater topography will be quickly erased by its flow. So focusing on Sputnik again. So again, this stuff is, yeah, it's plains of nitrogen ice, basically a nitrogen ice sea filling this enormous basin. We think probably reaching several kilometers thick, the nitrogen ice deposits here, and you can sort of see that kind of tapers into these southern uplands here. So one thing that immediately excited us when we got the first high resolution pictures down was that, well, firstly, there were no craters, so obviously an extremely young surface, but it was also the center and sort of northern part of Sputnik is divided into these cellular pattern, these ovoid cells. Typically, I think on average, the size is like 30 kilometers across, maybe the size of Marin County or so, and they're separated by this trough ridge structure. And given what we knew, well, just putting these together, the evidence, Sputnik Planitia, you can see it's very flat in the topography. There are no craters, and you know that nitrogen ice is very sort of low viscosity. We realized that what's happening is that just the sort of little bit of heat that's trickling out of Pluto's interior, well, it's not very much. It's actually enough to sort of heat up the nitrogen ice at the bottom of Sputnik Planitia and cause it to convex. So these are convection cells on the surface of this nitrogen ice sea. Warm ice is rising in the centers, moving to the edges, and then descending at the trough ridges. And we calculated that Sputnik Planitia can renew itself in just 500,000 years this way. So it's like a drop in the ocean in geological times. Yeah, any craters splatting into that is going to be eliminated pretty soon. If we go to the south of Sputnik Planitia, we exit the convective zone. We think that the ice needs to be more than a kilometer thick to support convection. So it's probably like kind of thinner out here when you get away from the actual impact basin part of the Planitia, which is probably where it's going to be deeper. But we still see no impact craters here, so the ice is still flowing. Instead, we see these swarms of pits here. Each of these dots here is a pit in the surface, probably up to a few hundred meters deep. And so this is where there's particularly active sublimation of nitrogen ice into Pluto's predominantly nitrogen atmosphere. Again, this is a little picture of what we're familiar with, sublimation on Earth, CO2 ice, dry ice, creating this mist as the ice sort of goes straight from solid to gaseous phase, skipping out the liquid. And we think they might be aligned, these pits, sort of in these swarms, due to being sort of stretched by sort of flow of the nitrogen ice. But the most explicit evidence we have for sort of flow of nitrogen ice is the edge where we see this. This is East Tomball Regio, kind of where the bladed terrain in the uplands here meets Sputnik Planitia, and where we have nitrogen ice is sublimated and redeposited on the uplands here. We actually see in a few parts these bands sort of aligned parallel to valleys connecting basins in the uplands here to Sputnik Planitia, and we realized that these are actually, these are active nitrogen valley glaciers on Pluto. These dark bands are the equivalent of moraine trails on Earth, where you get material eroded from surrounding mountains. It falls onto the glacier and is carried out, in this case, to the Atlantic Ocean in Greenland. We think the same thing is happening on Pluto. In fact, there are some little sort of bits of blocky debris I've mapped as this brown unit here that are sort of large kilometer-sized chunks of the uplands that have been eroded off, carried out in these cookie crumb trails, and then they're at the where it meets the convective terrain, they're always located at the edges of cells, so they're just getting like pushed around by the convection currents there. So in a way, this is kind of what I sort of think is like a cosmic game of rock, paper, scissors. It's like a hydrological cycle, but it's nitrogen in place of water. And instead of water ice glaciers cutting through rock, you have nitrogen ice glaciers cutting through like water and methane ice. So interestingly, you have similar landforms as on Earth, but out in this distant part of the solar system where it's kind of the role of the materials is swapped. So, okay, so all right, just a quick mention on the dark regions. So this stuff, so a lot of Pluto's equatorial regions are very dark, a very dark red color, and the largest is Belton Regio here, which I think is kind of Alaska sized in total when you consider its whole area. And this material, this dark red stuff, is what we call tholins. These are these complex molecules. They're mostly hydrogen and carbon, not exclusively, but mostly. And they're generated in Pluto's atmosphere. When you shine ultraviolet light on methane, it sort of creates these sort of these more complex tholin particles that form these haze layers in the atmosphere. You can sort of see them stretching above the surface here. And they gradually settle out across the surface of Pluto. And this happens everywhere, but they actually can accumulate to a thick blanket at the equator, which has a much more mild climate than the poles. The poles I mentioned experience extreme seasons, like 120 years of day and then 120 years of night. So you get a lot of volatilized mobilization between the poles across a year. So that basically would disrupt a tholin blanket. But at the mild climate you get at the equator, the climate is such that these things there isn't much volatile mobilization, and you can actually get these things building up to form this continuous dark blanket across the surface here. We think probably maybe about 14 meters thick, but I didn't map it as an actual geologic unit because it's just a little veneer that's sort of covering the bona fide units underneath there. So I might just rush through this because I guess we're coming up to an hour, but I figured to fill out the hour, I'd tell you a bit about Charon and the mapping that's been done for that. So this is Pluto's largest moon, Charon, approximate true view color, and just this gives you an idea of the real estate we're dealing with compared to North America. So if you were to unfurl all of Pluto's area, it would cover most of North America, whereas Charon would cover about half of the lower 48 there. Charon's New Horizons coverage of Charon, it's kind of the same story. We only saw one side of Charon up close, but since Charon was like more than twice as far away from Pluto during closest approach, the best images we have are only half as good as what we have for Pluto. We do have a topographic map. It was good enough data to get that for Charon, and we did get spectral data as well. But the thing is with Charon, it doesn't have the composition or diversity of Pluto. It's pretty much all water ice, but interestingly, we do see a few spots of ammonia at bright craters on the surface. It's kind of interesting because ammonia shouldn't survive for very long in the being sort of illuminated by sunlight. So the fact that it concentrates in these bright young craters, which are presumably quite fresh, means that these have been formed relatively recently, and the fresh sort of ammonia from under the surface is sort of exposed in the ejecta of these craters. So there's also been a mapping effort for this, not by me, but by my colleague at the Southwest Research Institute in Boulder, Stuart Robbins. He made a geologic map of Charon's near side. He published it in a Journal of Geophysical Research paper. He's not intending to publish it as a USGS map. But yeah, this is it. Here, he defined 16 units and a bunch of lineations and impact craters. But the thing about Charon is that it's much more, it has much less brightness contrast compared to Pluto. And so basically you can't really tell what on earth's going on the far side. It's just too sort of, it's too samey, sort of too homogeneous to really extend this mapping into the far side the way I could on Pluto. But most important thing to take away is that Charon is much, much older than Pluto's surface. So my person who helped map all my craters, Kelsey Singer, made these maps for Pluto and Charon. Each of these dots is an impact crater. You can see there's a lot in Pluto on the ancient Bernian terrains, but none on Sputnik or the bladed terrain here. It's a different story for Charon. It's sort of fairly heavily cratered everywhere it is. And so that means Charon's surface, or the surface that we can see, is universally very old, probably about 4 billion years old. There's not the sort of massive range in surface ages that we see on Pluto. And so, yeah, Stuart put together a little similar stratigraphic column for this for his 16 units, and he divided them into 3 periods, the Ozian, Vulcanian, and Spockian. And yeah, you can probably gather that the nomenclature system on Charon is the nerdiest in the solar system. Although they have the International Astronomical Union hasn't actually confirmed quite a lot of names on it yet. Often the sci-fi and fantasy names are still waiting. Maybe there's like copyright issues and such to deal with there. But you can see these ages, yeah, like he sort of just reckoned Ozian more than 4 billion years old, Vulcanian about 4 billion, and Spockian less than 4 billion. So pretty much everything that happened on Charon was a lot very old. But a lot did happen. I'll just run through these quickly. It's basically, Charon, it's a story of 2 sort of types of terrains, really. The first is Ozterra. So looking down on the North Pole, this is mostly taken up by this unit BL, which he called a blocky terrain. And these 10 high-standing plateaus, hundreds of kilometers across, separated by troughs tens of kilometers wide. You can maybe, at least some of you in the front, just see what's going on here. The lighting angle was quite high in the sky, so you can't really see all shadows here. But there are sort of some of these troughs I've tried to indicate with yellow lines here, separating these blocks. It's actually much easier to see in this topography map here. This is Ozterra. You can sort of see it's divided up into these sort of separate large blocks, the crust here. And we think this probably formed this texture, large-scale texture, the same way that the cracks on Pluto formed. Charon once had a sort of a subsurface ocean that gradually froze and caused Charon to burst its skin as the water turned to ice and expanded. The most sort of stupendous way in which Charon's surface seems to have cracked is these enormous fracture belts that extend from roughly southwest to northeast across its surface. And these things are much larger than most of the fractures we encounter on Pluto. They include these enormous graben I mentioned before, but here's an actual image of one where you have 2 normal faults with a sort of a sunken block in between. That's what we think Serenity Chasma here is, sort of bordering Ozterra, sort of at its southern end. You can also see it in the topography here. So yeah, this is Serenity Chasma, extremely deep, 5 kilometers. There are a couple of, maybe a bit hard to work out, but he's mapped as this separate unit. LA1, what look like these lobate aprons, we think are actually landslides that have the surfaces on the steep edges of the canyon are unstable and so have sort of fallen away to create these landslides here, which you think are some of the very few Spockian, that is somewhat younger features on Charon's surface. And this thing quite here, this mountain block, which is marked unit MOC, you can sort of see it about here. It's kind of interesting because it looks like a bit of the Ozian crust that is sort of like a tilted block. It's sort of tilted and sort of tilted and sort of almost sunken into Vulcan Planitia here. And I say sunken because that's kind of what the hypothesis we've come up with to explain Vulcan Planitia. So this is the other sort of major geologic province on Charon. You'll notice here, this is Ozterra up here. Vulcan Planitia is much smoother and flatter here, generally about 1 kilometer lower in elevation than the blocky stuff of Ozterra up here. And it has this interesting features we haven't really seen anywhere else in the solar system, these moated mountains. So this is the surface of Vulcan Planitia here, this smooth terrain he mapped as unit SM1. And you can see Kubrick Mons here, it shows quite well in the low lighting angle here. It's sort of this high mountain, but surrounded by this deep moat, a few kilometers deep. And the same thing is going on with Clark Mons here. And we also noticed around the edge of Vulcan Planitia, you can sort of see this dark band here. There's sort of this deep trough that extends around. So to explain this, the fact that it's so flat and sort of it seems to be in some cases embaying topography, that these may actually be enormous giant flows of water ice cryolava that erupted from underneath in Charon's interior early in its history, perhaps even released by the enormous fracturing that occurred along the edge of Oz-Terra here, and kind of just spread out across the surface in kind of the same way that the lunar maria formed. Sort of the dark parts of the moon are thought to have formed by big outpourings of basalt early in the moon's history that filled sort of impact formed depression. So we think maybe possibly a similar thing is happening here, and that as this flow advanced across the landscape, it sort of may have embayed pre-existing topography. Maybe these are pre-existing mountains that the sort of the thick, sort of gloopy cryolava just sort of stopped short of it as it sort of advanced across the surface. But maybe they're also potentially like founded blocks of Charon's crust that's sort of kind of carried away sort of in the sort of passage of these cryolavas. We're not quite sure, but just the fact that it's sort of so flat compared to this what is, we think, slightly more ancient terrain of Oz-Terra up here does make us think that this may be some sort of giant cryolava deposit of some kind. And then the very last slide of Charon. I've just got a few slides left, but this thing, he didn't actually feature it as an overlay in his map, but it's one of the most characteristic aspects of Charon, because it's very rare in the solar system to see a dark pole. This area Mordor macula is this sort of dark circular feature, so that's centered at the North Pole of Charon, sort of quite dark in the center, sort of getting lighter towards the outside. And we notice it has this distinct reddish tint that indicates the presence of tholins, like those in the equatorial regions of Pluto. But of course, Charon, it has no atmosphere, and we haven't detected methane anymore at the surface. So if these are tholins, which we think derived from methane, then how did they get there? Well, we measured, actually, when we flew by Pluto, that its atmosphere is slowly escaping. It's slowly being stripped off by solar wind, and also Pluto isn't that large, doesn't have much gravitational force, so it is slowly losing its atmosphere over the as it ages. And Pluto and Charon's orbit, there are a few times around their orbit around the sun that Charon is actually downwind of Pluto relative to the solar wind. So there are a couple of times it's being subjected to this sort of stream of escaped atmosphere from Pluto, and some of this is going to be methane. So we think that actually it's capturing some of this methane from Pluto that sort of settles across its surface and is actually sort of and is kind of being trapped in cold traps at Pluto at Charon's very cold winter pole. Now in summer, a lot of this will sublimate away, sort of because it gets quite hot, but we think some of it is actually sort of deep frozen into the water ice crust here and kind of remains to be processed into tholins there. And I think the departure imaging, we could just get some very dim images, or maybe it was just like looking at the thermal signature of Charon's south pole, and we reckon there's actually a corresponding dark pole at the south. So yes, Charon does have these two dark red poles of captured tholins from Pluto. So, all right, this is just summarizing, I guess, what happened for both of these places. So, yeah, Pluto turned out to be far more diverse than we ever thought, and a lot of that is because it's managed to hold on to its atmosphere, largely because it's sort of continuously sublimating and redepositing these exotic ices on its surface. So it hasn't really managed to lose its atmosphere, because it's half the time its atmosphere is bound up as ice on the surface. Its Sputnik Basin was like very important in defining the remainder of its geologic history. All of its nitrogen ice pretty much ended up there and resulted in this true polar wander. And then you basically have successive mantling events for the remainder of its history, first in Hayabusa, and then these very thick deposits creating the Tartaran deposits at the equator, and possible via cryovolcanism. And then Sputnik Planitia has just been doing its thing of going resurfacing by convection and sublimation and redeposition for the last 4+ billion years. And so Charon does seem to have had a busy geologic history very early on, but it's very small. It evidently didn't retain an atmosphere. If it ever had a lot of volatile ices across its surface, it didn't retain them. So it's basically, it sort of just, it was a bright spark early on, but it then lost its if it didn't have any more volatile ices, so there was no real means to sort of maintain geologic activity. You can't really do much with water ice at these conditions. It's too hard to mobilize. So it's been essentially dead for the last 4 billion years. And then I'll just leave with this slide, which I think conveys the spirit of discovery that we all felt 10 years ago. It just went in the space of a few days from this sort of just a few dots in the sky to these fully fledged, amazing worlds. And it's, I guess, a big aspect of this conference last week was just how much diversity is there out there in the Kuiper Belt. We think there's probably quite a lot. We can see these sorts of odd ices on a lot of other Kuiper Belt objects. So it's just damn hard to get to. So maybe one day we'll get a better idea up close of just how amazing and special this distant part of the solar system is. So that's all. Thank you very much.
Thank you very much. Okay, we'll go ahead and open up for questions.
Okay, I guess the farthest one out first.
Hi, thanks for the very nice talk. I have two questions. So one of them is about the origins of this binary planetary system. So did it happen through impact or capture? And the second is how you can assign absolute ages to these geological units. So I understand how that can be done in the inner solar system, where we have like radiometric measurements from rocks that we got from the Apollo missions.
Yes.
Right. But it's like, are those extrapolated to the outer solar system as well?
So I guess firstly the binary, we have detected out of all the Kuiper Belt objects we've found so far, quite a lot of them seem to have at least moon systems. So at least even if they're not sort of similar size as Pluto and Charon to each other, a lot of them do have moons. I know that as for like sort of planetary formation, I'm not so schooled in, but I do know that a lot of modeling shows that formation of these binaries is quite common, sort of so as you sort of get sort of collapse of material in the sort of proto-solar nebula. Often you can get two large objects circling each other, and the next object that it encountered farther out, Arakoth, is an excellent example of that. It's a contact binary, which we think is two objects that initially formed and other objects were sort of expelled from the system, leaving just these two together. So yes, I mean, it's...
But then you still have to explain the asymmetry in composition, right? Because if they form next to each other, why?
So in the case of, I guess what I'm referring to when you say binary, I'm referring to stuff like Arakoth. Pluto and Charon, we think actually probably formed more like the Earth-Moon system, a giant impact into Pluto that skimmed off sort of a lot of material that recondensed around Charon. But for actual true bona fide binaries like Arakoth, so I think that the modeling shows that kind of at that scale you do get quite a lot forming, and we think that there actually seem to be quite a few comets that are binaries. So comets, we think quite a lot are sort of perturbed on their orbits, and there may be Kuiper Belt objects sort of coming on the inner solar system. I mean, I know as for absolute ages, I will say up front, there are some quite large error bars. I mean, we don't have the benefit of getting samples from the moon, and it's really ultimately a question of just assessing the impact flux in the outer solar system, which we can do just by observing sort of how much stuff there is out there, but also there have been like models, like originally the Nice model, generated by this guy Alessandro Morbidelli in France, in Nice, hence Nice model, to sort of define the history of the early solar system in terms of like how much sort of impactors you would get at different parts of the solar system. So it's modeling like that, and I mean Pluto has been a help and Charon have been a help in allowing us to see for the first time in the Kuiper Belt how many craters there are and get a better idea of how much stuff is flying around. So I mean, for me, I basically hired out people who sort of do study impact fluxes, and basically, you just relate sort of the number of craters you've counted to the expected impact flux to get these ages, and that's kind of the best we can really do until yes, you could actually get samples, although, yeah, I'm not quite sure what in them radiogenic stuff in them would help you, but yeah, that's pretty much where you have to go on. Yeah.
Right, thank
I
you.
think next to you.
Yeah, so the Sputnik basin, does the fact that one edge of it is kind of undefined, does that give you an indication of the direction of the impact?
So, yeah, there's actually kind of two elements. We think, in fact, this is one of the latest results. We presented this last conference. The impact, the basin, the ellipse itself is, well, yes, it's elliptical. So we think that the oblique impact probably came either from this direction. It came in this direction, either from up here or down there. So, however, the tapering section at the southern end, and the topography, we've realized that there's actually what looks like an enormous rift down here. This is something that I guess we've just come up with recently. I haven't mentioned it in the geologic map, but there's this enormous scarp here, sort of, that reaches like 5 kilometers high. So it's what we've called the South Sputnik Scarp. And we think that that actually may be a separate tectonic system that opened up shortly after the Sputnik Basin formed. My colleague, he does the modeling of stresses imparted on the crust by true polar wander, and he finds that there's actually quite a lot of extensional stress should result after true polar wander at the southern end of the Sputnik Basin, where we see this rift. So, yeah, so we think that maybe originally there was a complete basin rim, but that this rift opened up at the southern end and basically eliminated the rim and caused the nitrogen ice to spill over into this rift. So, yes, that's what we're pondering at the moment.
Yeah, the other quick question is, New Horizons visited Arakoth. Is there any other targets possible?
No, not at the moment. I think there's still a hunt going on, but it's like really kind of unlikely now. It's more than 60 AU away. It's now farther from Pluto than Pluto is from Earth. Yeah, so we've got like the Subaru telescope and Mauna Kea doing a search, but yes, hasn't found anything so far. Yeah.
Hello, have a couple of questions about the ice in the craters. So you say the nitrogen ice is mobile and kind of flows.
Yes, yeah.
So if it's impacted, would it leave any craters, or would it just go splash and settle back?
Yeah, it would leave a very transient crater for, I'm sure, maybe decades or maybe hundreds, maybe thousands of years at the most. But then it would just, I mean, you don't even need, convection would speed up the process, but even when it's not convecting. I guess one thing I say to like high school kids when I sort of give a talk like this is that something on Earth easier to compare it to is tar pitch. So there's like the Queensland tar pitch experiment where they put some pitch in a funnel in the 1920s, and then since then 9 drops have fallen into a beaker below. So it kind of, on a short time scale, if you smash it with a hammer, it would behave brittly, but over hundreds, thousands of years, it would just flow. So I think a crater would not really exist beyond that sort of time scale.
So how much of the surface is covered by the nitrogen ice compared to the methane ice?
Only, I mean, in terms of area, given that most of the nitrogen ice is concentrated in the Sputnik Basin, just very thick. I mean, much less nitrogen than methane. Methane is to some degree, I mean, that's kind of the volatile ice that coats the rest of the highlands to varying degrees. It can be quite thin in the west, but getting much thicker to the east. So it's definitely the more representative sort of deposit across the surface at large. Yeah.
And then finally, are the craters or the whatever's impacting, or do they come from the same direction? Are they coming from the Kuiper belt, or are they coming from all directions? Do you know?
They're what I guess we call heliocentric impactors. So it's just more Kuiper belt objects orbiting around the sun, really, that would crash into it. Pluto doesn't have a very high gravity, so stuff would have to get really quite close in for it to pull on it enough yeah. So it's really just other little Kuiper belt objects out there. It's possible, actually, it's hypothesized that it may have actually formed, this is yet another aspect of it, it's a resonant Kuiper Belt object. It's actually, there are a bunch of these that are in a 3-2 resonance with Neptune's orbit. They orbit twice for every 3 orbits that Neptune makes. And we think that a lot of these things, they're called the Plutinos after Pluto, they're actually shepherded into their present orbits by Neptune, and they actually may have been formed originally closer into the solar system where the impact environment was higher. So, yeah, the stuff they impacted in, and they themselves may have been closer into the solar system originally. Yeah. I think, do you have, no, you didn't, oh, over there, okay, yeah.
I had questions about Charon.
Mhm.
What is the tilt of the axis on that, and how long are the seasons on that?
It's the same. So yeah, since they're in a binary planetary system, they share the same like orbital plane around each other. So they share the same mass, enormously long seasons. Yeah.
And then the second part of my question is, what are the seasonal temperature differentials from, say, like the dark side and the equatorial and the polar?
Yes. Okay. I'm trying to think of a graph that someone made for this. I mean, in general, like the highest it gets is sort of not more than like 40 something Kelvin, and we're talking sort of differences of like maybe 10 Kelvin or so. Yep. We think so. Yeah. I guess another complication of Pluto is that under 19 degrees is its current obliquity, but I think its obliquity actually changes on a cycle between like 98 and sort of 127 over a 3 million year cycle. And that means the solar illumination that the surface receives changes over that cycle. And so some parts suddenly become less conducive, or less and more conducive to like sublimation and deposition of nitrogen ice. And that will cause, maybe sometimes there are parts in the obliquity cycle that you get a lot more sublimation, and the atmosphere pressure can probably increase maybe orders of magnitude. It's currently about 100,000th the pressure of Earth's, but it may indeed change by orders of magnitude, and that can probably change the temperature, so the surface as well. So yeah, yeah, there's a lot going on to move those volatiles around.
Any other questions?
Yeah, I was kind of curious about the logic behind the naming of geological ages and geological features. Seems to be a wide variety of choices there. I'm thinking of like Sputnik,
Yes.
Lucada, and then modern people and so on.
Yes, so the USGS Planetary Gazetteer website sort of includes the naming systems for all of these. But yes, you're right, there has been a range of different naming themes for different types of landforms. So Planitia and such, like sort of plains and things, the theme has generally been spacecraft. So there's like Venera, Vega, Rosetta, and yeah, Sputnik. And there are also like the major regions have been named after prominent Kuiper Belt scientists, like Tombaugh Reggio is the big heart, sort of which Sputnik is the left half, and Tombaugh and Lowell also gets his region. So yeah, and there are also like various underworld deities and like mythological travelers as well. So yeah, quite a few different naming themes for Pluto, and also for Charon, where, as you saw, it's kind of tended a bit more to the fantasy sci-fi side. Yeah.
So the USGS is kind of the main body
Yes.
for discoveries from the United States. What about discoveries from other nations and their naming? What controls that?
It's still the International Astronomical Union, so they
International,
control,
okay.
they're the final
I see.
arbiter of all.
So all
names.
these things had to pass through
Yeah,
them too.
we have to like write out proposals for naming, and like why it should be named as such, and why it should be a Planitia or a Montes, and it has to be run by them before it's made official. So some of these names I've shown you are official, some aren't. Most of the ones on Charon aren't, although Clark and Kubrick are, thankfully.
Is that Arthur C. Clarke
Yeah.
and Stanley Kubrick?
Okay, thank you, Dr. White. We're going to conclude the meeting.
Thank you.
Thank you so much for joining us. That was truly fascinating. All right, we'll see you guys up on the mountain. Clear skies.
I guess it's called a lot of geology. Sorry.
I'm learning a lot, thank you.
Oh, you're welcome. Yeah.
Appreciate it.